This is just a pile of white powder sitting in a porcelain dish. It looks completely inert, but the second a lighter flicks on and touches the edge, the powder erupts. A dark, writhing column of ash coils like a living thing. Discovered in 1821, this reaction was dubbed the Pharaoh's Serpent. The coiling column looks exactly like a snake rising from a basket in ancient Egypt. The original 19th century version relied on mercury-2 thiocyanate. It was a staple of magic shows and parties, but it produced cyanogen gas and left behind this toxic mercuric sulfide residue. To get the visual impact without the mercury poisoning, modern chemists had to reverse engineer the thermodynamics using safe household materials. The modern substitute uses a ratio of 4 parts powdered sugar to 1 part baking soda, piled onto a base of alcohol-soaked sand. We're going to run this safe version and pause the tape to dissect the chemistry at the molecular level, second by second. This reaction is a highly orchestrated chain of thermodynamics and gas physics. Let's start the clock. At T-0, the powder is kinetically stable. Its molecular bonds won't break on their own. They require a specific deposit of activation energy from the lighter's flame to start the sequence. By T+15 seconds, the sugar begins to combust. This burning sucrose acts exothermically, releasing a massive payload of heat. This heat forces the baking soda into an endothermic decomposition, absorbing the energy and violently releasing carbon dioxide gas. The sugar provides the engine, and the baking soda provides the payload. Once ignited, the reaction becomes entirely self-sustaining, continuing to rapidly grow upward without any further help from the lighter. At T+60 seconds, the newly freed carbon dioxide gas nucleates into microscopic bubbles inside the molten sugar matrix. This triggers anisotropic gas escape. Because the softest material is at the base, where the heat is most intense, the gas pushes through the path of least resistance, driving the column vertically. The coiling happens because the growing foam is structurally unstable. A steep thermal gradient exists between the hot base and cooling top, causing the fragile tower to bend as it is pushed from below. The living movement of the snake is simply trapped gas pressure, constantly fighting against the structural limits of the carbon tower. At T+3 minutes, the sugar fuel finally burns out. As the temperature drops, the column hits its maximum height and stops. During the cooling phase, the partially burned carbon soot from the sugar solidifies. It forms a rigid framework that freezes in place around the trapped carbon dioxide bubbles. This structure is similar to low-density materials like aerogel. The final volume is almost entirely empty air, held together by a microscopic skeleton of soot. The finished serpent is essentially frozen snook, a hyper-fragile architecture of carbon and air. While the column's volume exploded to 15 times its original size, we still have to account for its physical mass. Our weigh-in data reveals that the final snake actually lost 26% of its original mass compared to the starting powder. This illustrates the conservation of mass. The missing 26% simply floated away as carbon dioxide and water vapor. The reaction didn't create new matter. It used thermodynamics to radically rearrange the density of what was already there. Industrially, this swelling, heat-activated chemistry is known as an intumescent reaction. This same foaming action is used in fireproof paint. In a building fire, the coating expands into a carbon foam that insulates structural steel beams, preventing skyscraper collapses. The Pharaoh Serpent reaction demonstrates how matter releases stored energy in a predictable, physical way. To see us forensically dissect more chemical reactions, subscribe to Galvix Science and drop a comment letting us know what we should investigate next.